Welcome to The Explainer. I'm your host, and today we're going to completely flip how you look at the physical universe. We're diving into the real rules of work, energy, and power. Okay, let's just jump right in with a quick reality check. Imagine you're pushing against a heavy, rigid brick wall, right? You do this for hours. You're sweating, your muscles are literally shaking, you are absolutely exhausted, and you feel entirely drained. But from a strictly physics perspective, how much actual work did you just accomplish?
Mathematically speaking, you've done exactly zero work. Zero. I know, it's a completely shocking truth. It kind of forces us to unlearn our everyday vocabulary if we really want to grasp physics. See, your muscles are alternately contracting and relaxing, and you're definitely burning internal energy, which is exactly why you feel so wiped out. But since that wall didn't move a single inch, the physical work done on it is just a big fat zero.
So, to make sense of this paradox and build up to the ultimate rule of the universe, here is our roadmap. First, everyday words versus physics meetings. Second, the vector math decoder. Third, defining work and motion. Fourth, the work-energy theorem. Fifth, storing energy as potential energy. And finally, number 6, conservation of mechanical energy.
All right, Section 1, Everyday Words, Physics Meanings, Unlearning Our Language.
There is a massive divide between how we talk normally and the actual language of the universe. Like in everyday life, we'd say a farmer plowing a field is doing work, or someone working a 14-hour shift has crazy energy. We'd even call a really fast karate punch powerful. But physics is way more strict. Work absolutely requires displacement. Energy is precisely defined as the capacity to do that work, and power is literally just the rate at which that work gets delivered. So yeah, there's a pretty huge gap between our everyday feelings and the rigid laws of physics.
Section 2, the Vector Math Decoder, our secret tool.
So before we completely redefine these concepts, we kind of need the right language. Since physical quantities like force and displacement are vectors, meaning, they have both a magnitude and a specific direction, we have to know how to multiply them properly. Here's the catch. Multiplying two vectors doesn't always just give you a new direction. Instead, we use something called the dot product or scalar product. This gives us a simple, single number, a scalar, based on the angle between those vectors. You basically just multiply the magnitude of vector A by the magnitude of vector B, and then multiply that by the cosine of the angle, theta, between them. If you picture this visually, you're essentially projecting the shadow of one vector right onto the other one. It tells you exactly how much they are working together in the exact same direction. Think of it like pulling a toy wagon by a string at an upward angle. The entire force of your pull isn't actually moving that wagon forward, right? Only the geometric shadow, that horizontal projection of your force running along the ground, is what's actually contributing to the forward motion. The dot product captures that exact relationship perfectly.
Moving on to Section 3, defining work and motion, the blocks of physics.
Remember our brick wall from earlier? Work is only done when a force causes displacement. In fact, there are 3 totally wild scenarios where physical work is exactly zero. First up, zero displacement. A weightlifter holding 150 kilograms completely steady on his shoulders for 30 seconds is doing zero physical work. Crazy, right? Because nothing is moving. Second scenario, zero force. Imagine a block just sliding endlessly across a perfectly smooth, frictionless ice rink. It's moving, sure, but no horizontal force is actually pushing it, so zero work is being done. And third, this is the real mindbender. If force and displacement are mutually perpendicular. Think about the moon orbiting the Earth. The moon moves tangentially, but Earth's gravity pulls straight inward. Because the angle between them is exactly 90 degrees, and the cosine of 90 is 0, Earth's gravity does absolutely zero work on the moon.
Now, when work is successfully done to create motion, it shows up as kinetic energy. This is the energy an object has simply because it's moving. And out in the real world, this energy scales up dramatically. To put it in perspective, a tiny 1-gram raindrop hitting the ground at 50 meters per second holds a really delicate 10 to the negative 3 joules of energy. But take a 50-gram bullet traveling at 200 meters per second, that packs a staggering 1,000 joules. The capacity to do work scales massively depending on speed and mass.
Section 4, the work-energy theorem, linking force to motion.
Let's actually walk through how this builds step by step. We kick things off with a basic equation for rectilinear motion you might remember from early physics. Final velocity squared minus initial velocity squared equals twice the acceleration times distance. Now just multiply both sides by half the mass. By substituting in Newton's second law, mass times acceleration equals force, we magically arrive right at the work-energy theorem. It simply states that the change in kinetic energy is exactly equal to the net work done on the object. It's this perfect, seamless bridge between the invisible forces we apply and the visible motion we actually see.
To make this a bit more tangible, imagine a ballistics demonstration. Say a police officer fires that 50-gram bullet we talked about into just 2 centimeters of soft plywood. The negative work done by the wood's friction perfectly accounts for the massive drop in the bullet's kinetic energy. That friction violently opposes the motion, literally stripping away 90% of the energy. Because of that, the bullet's speed plunges from 200 meters per second down to just 63.2 meters per second. That loss of energy is an exact, perfect ledger of the negative work done by the wood.
Section 5. Storing energy, potential energy, and variable forces.
Here's the thing, though. Constant forces are actually incredibly rare in nature. When we deal with a variable force, like say a stretched bowstring that gets harder and harder to pull the further back you draw it, we calculate the work by finding the total area under the force curve. We estimate this by just adding up all these tiny rectangular slices of displacement. And the really cool part, if we make those slices infinitely small, they converge into the exact area under the curve using calculus. It's a pretty beautiful mathematical evolution.
Now, what happens when work is done against conservative forces, like gravity? Well, it doesn't just disappear. It gets stored up as potential energy, which we denote as V. The word potential literally suggests the capacity for action. So, if you hoist a heavy mass up to a certain height h against gravity, you are banking energy equal to mass times gravity times height, or mgh. It just sits there, stored up purely by virtue of its position, entirely ready to be unleashed as kinetic energy the absolute second you let it go. And finally, Section 6. Conservation of mechanical energy. The grand finale. When a ball drops off a cliff of height h, it is simply trading in its banked potential energy for kinetic energy. Right at the very top, before it drops, its energy is entirely potential. Then just a split second before it smacks the ground at height 0, it is entirely kinetic. But at any given height h, right in the middle of the fall, it has a mix of both. And the truly breathtaking part about all this? The total sum of kinetic and potential energy remains perfectly, exactly constant throughout the entire fall. It is just an exquisite mathematical balancing act. Which brings us to the ultimate unification here. Energy is never truly created or lost in these systems. Never. It merely trades places between motion and storage. As long as you were dealing with conservative forces, the sum of kinetic and potential energies, the total mechanical energy, will always be conserved. It is quite literally one of the deepest, most reliable rules governing how our entire universe operates. So, as we wrap up this explainer, I want to leave you to ponder a somewhat terrifying but completely fascinating reality. The Earth's crust has massive dislocations called fault lines, and they essentially act like giant compressed springs. They are conservative systems banking colossal amounts of potential energy over decades, even centuries. Knowing what we now know about how potential energy must eventually manifest as kinetic motion, what happens to all that immense stored energy the absolute moment that fault line finally snaps? Thank you so much for joining me today. I hope this changes how you see the invisible forces shaping our world. Keep questioning and keep learning.